researcher in very interesting combustion studies. After studies in Moscow and Odessa, thanks to a Marie Curie program, he ended up in the Netherlands and has been contributing to the research in the Netherlands for many years. And he writes in his own words that his research interests include combustion of metals, premixed gas flames, mechanical alloying, and electrodynamic fluidization of conductive powders. And that's exactly what people who were seeing the lab tour a moment ago would already. So people have attended the lab tour, have already seen the experimental experiments he will talk about today is, okay, if you do experimental research, what are the other things you have to think about? And anyway, we don't know what will be the topic, but the topic is focusing on the flames and some practical tips for flame diagnostics. So after the lecture, you can ask questions, and the people who are online, also 10 people online or more, they can ask questions eventually through the chat. But first, we give the floor for 3/4 of an hour to Yuriy to explain the message to us.
Thank you for introduction. Good afternoon, everybody. And first, I would like to thank Dick Rukers and Rob Batten for inviting me here for their presentation. Initially, they asked me to actually present some experimental techniques, but then I was thinking about including some research story in this presentation. So that's why I wrote this abstract. But when I started preparing that, I found that there is no place for that. So there will be some illustrative examples, but not actually real discussion of some scientific results. So that's why it's maybe more boring than expected, but still I hope that there will be some use of that presentation. So I will start. I will discuss only like simple, relatively simple and well-known diagnostic techniques, but to apply them, it's good to know some things which usually is hard to find in the publications, because maybe people think they're too simple, or they explain too short, or they are missing them. And then we just want to apply something. Just all my students, they ask the same questions, and so that I just decided to share some tips about these techniques. So I will start with particle image velocimetry, then continue with interferometry for flames, which includes regular holographic interferometry, digital holographic interferometry. Then laser, briefly mentioned that laser attenuation method for measuring aerosols, and particle size measurements by attenuation, and relay scattering for flame smoke confinements. And if there is still enough time, I can try to discuss the also multi-color or colorimetry with color cameras, which is often used to, or attempt to use for dust flames. So first, particle image velocimetry. So I think that everyone has a general understanding how it works, but still I would like to remind maybe that the particle velocimetry allows to measure two-dimensional velocity field, and in particular in flames. And if you have like radial symmetry or 2D flame, then you can just recover the total velocity field. So for this flow of reactants is seeded with fine particles which follow the gas actually, and then illuminated with a laser sheet. Typically, it's a so-called cross correlation is used, which is in which particle illuminated twice, and the images are taken on separate frames. To do this, you need some special equipment, which is often or expensive, and not every lab has. So the way velocity is determined is that one of the images is split on so-called small interrogation windows, which contain some number of particles, and then this image of this window is shifted toward all directions over the second image. And when the best correlation is achieved, this displacement is taken as a particle displacement, gas displacement. There is another method also which is called autocorrelation, when 2 or more exposures are done on the same frame, and actually the correlation is the process the same way, but the interrogation window is shifted over the same image, just zero shift is excluded. And autocorrelation in many cases actually can be not only cheap, but also advantages for the PAV method. One important thing that the software always looks for correlation. It doesn't track single particle. So it can be, you can have image crowded with particles. You may not tell one particle from another, but it's even better. The software will work. And what usually is measured and can be measured by particle velocimetry in flames. First, most often it's applied for burning velocity measurements, which are low. It's called let's call it burning velocity. Other important parameters which you can extract for this measurement is flame stretch rate. It's not so often used, but very useful value is so-called dilatation rate, which is a measure of local thermal expansion. And because the thermal expansion happens only where reaction takes place or intensive heat transfer takes place, then it has essential value only in the reaction zone and preheat zone. So you can detect the actually cold boundary and hot boundary with dilatation rate, but in general you cannot detect any kind of isotherms otherwise in between, because if flame is stretched and curved, there is a complicated dependence between dilatation and temperature. Dilatation rate also allows to calculate absolute heat release rate per unit of flame front area, or for the total flame. And even temperature field can be inferred from these measurements. In some cases, even so, this may be not good quality, but for some purposes, it can be enough quality. And then there are just just say some more words about autocorrelation. So that in the autocorrelation, you can use actually any camera, not a dedicated PAV camera. But if you have global shutter, then you expose the total image. It's like very short, short exposure time. But most cameras have rolling shutter. They expose line by line. But still, for most like laminar flames, even rolling shutter camera, this is the camera which you can use usually at home, that it can work. And the advantage is that you can actually use first, these cameras have typically much higher resolution than PAV cameras. So the one thing, that's another thing, that if you study steady-state flame, then you can actually expose one particle not 2 times, but 20 times or 100 times, as many times if you want, and then you can minimize the seeding density of the flow to minimize disturbance of the flow. This is an example of such measurements. Here, this is the flame which affected by barrier discharge plasma. It's stabilized above the perforated plate, and there is a discharge in every cell of this plate. It has complicated structure, and then you don't want particle to affect this discharge, and you want them to settle in this cell, so that we want to minimize the particle concentration, and for this purpose, the autocorrelation works quite well. So here, every particle is exposed like 50 times, so have real seeding density is small, but the one which you process is high. So I think that with autocorrelation, everyone can do without dedicated equipment. Another, actually, I don't know if we can call it problem, the laser sheet. Actually, if you read article, then you usually read that, okay, laser sheet was built with cylindrical and spherical lens, that's it. But in illustration, you very often see the divergent laser sheet. But for laboratory flames, many flames are stabilized like close to, for example, burner rim, or stagnation flame close to some stagnation plate, and you want to move measurements as close as possible to these obstacles, and then you cannot use the divergent laser sheet. Another thing that you often want to use, if flame is small, or you use some small element of flame, you want to focus actually the minimize the laser sheet thickness. And it's not a big deal, but still, if you are new to this, that there are usually that there are a lot of questions how to do. And it's not to do this. You need cylindrical and spherical lens. Better use a good quality spherical lens, but still like regular planar convex lens also can work. And you can see just from this drawing that if your focal points of cylindrical lens and spherical lens coincide, you have parallel laser sheet. So this lens should be strong enough to expand beam for the full aperture of the spherical lens. And then you have parallel beam, you can always put some screen to block the radiation which actually comes onto the structural elements of your burn. And then if you look from the top on this laser sheet, we see that cylindrical lens doesn't change direction of in this projection of the laser beam, and then just you simply put your flame in the focus of this lens, and if you, depending on the size of the flame, you want to also to be the thickness of the laser sheet to be uniform on the flame. So it means that if your size is bigger, you need longer focal length. And for small flames, it can be shorter one. And here is an example of using such focused laser sheet. This is just the small element, the base of inverted flame, methane air flame stabilized by 2 millimeter diameter rod only. So then, and I was interested actually in the structure, flow structure in the flame base below, in particular the vortex. Here, so, and with this, like if you just make this well-focused parallel beam, then you can just approach very close to this holder, and you can see that holder is only 2 millimeters, but velocity measured in very details. Another problem that actually people who try to do, many flames can be stabilized in tubes, or you need tube just for propagating flames, or for example to protect flame from environment. And if you try to do PIV in tubes, there are always like two bright strips you see on the background. And that's I was in the 2 labs, worked, and my colleagues said that just took it as like inevitable evil, and they think so you have to live with that. But actually, it's a very simple way to get rid of that. So that this is just schematic of their like all reflections which you have during PIV measurements, and the main strips, they appear due to laser scattering on the walls, which reflected on the 2 sides of the back wall, and there are also side strips, but they are close to the edge. So if you just paint from inside the back wall, you get rid of that. And there are some strips remaining here, but usually this is a dead zone. If you still want to ultimate solution, remove everything, then you just can remove the segment of the tube and put flat windows with some black paint or black silicone glue. Then this light also doesn't penetrate inside the tube, and you don't see this strips. This is very simple, but actually I got a bet from one even optician who, for a bottle of cognac, that it's not possible to solve it. That's very strange. And one of the most important parameter which can be measured for in flames with PIV is burn velocity or flame speed. and the local flame displacement speed is defined as difference between the local gas velocity and the flame front velocity multiplied by the normal vector to the flame front. And this is the velocity of the hot gas. And then, but the value of interest is so-called density normalized displacement speed, which is, I call it burning velocity. Maybe it's not quite correct, but it's much shorter to call it like this. And this is if you just measure velocities in the flame, first you are interested in this value for reaction zone, because most of, for example, stretch theories, they are most consistent for just written for the reaction zone. Also, just the very word burning velocity means that this velocity relates to the location where fuel is burning. And typically, what is measured this value is measured for the close to the preheat zone, so the cold boundary, which is not so relevant to burning velocity. And hot boundary, you need to know density, and this means need to know temperature, which you usually don't know. However, for steady state flame, there is a way to overcome this problem. So if you look at this equation, for steady state flame, velocity of the flame front is 0. So the displacement is simply local velocity times to unit normal vector to the flame front. I just omit minus because we are interested in positive values. And this should be normalized by density ratio. And this can be done using continuity equation along any stream tube. So by stream tube, if this is a drawing for 2D flame, but if you have axisymmetric flame, the stream tube actually is the body of revolution of this tube along the symmetry axis. So the continuity equation says that the mass flow through any cross section, which can be also put at any angle to the strip tube, should conserve, so that we just can write the mass flow for the cold location before the flame, and that should be equal to the mass flow at the location of the flame front. We can take any location, preheat zone, reaction zone, or something in between, but this always holds. And from that, we just can find normalized displacement speed, which is actually the velocity measured at call sign times unit vector normal to this velocity and times to the ratio of these stream tubes areas. And it can be done even simple, because we are free to select the angle. We just select the horizontal, and PAV measures vertical and horizontal components. So then, in case we just use the vertical component of the measured velocity, and it becomes that simple. So, but for some reason, it's rarely used. So here are some examples of measurements of burning velocity with this method. This is the limit flame of the methane air flame propagating in standard flammability tube. So it's steadily propagating. So if you subtract flame speed, it becomes steady state flame, and then you apply this stream tube method. Also, stretch rates along the flame were derived for that flame, and so this is our burning velocity along the flame for different concentrations. So this is the velocity of the symmetry axis, and they're defined for the cold and hot boundaries, and hot boundaries in turn were defined by dilatation rate. So then you see that for limit flame, the burning velocity at the cold boundary is just 1.5 centimeter per second, and it would be very difficult or even impossible to extract it by any other method. And the velocity at the cold boundary is several times higher. And they also see that stretch effect is opposite to the cold and hot boundary, because when stretch decreases, these two values convert to some intermediate value. This is another example of using stream tube methods. Was done in our lab here, that the flame stabilized in the like ionized flow. I mentioned before that this barrier discharge plasma, and in that case, actually we cannot apply this method to the cold boundary, because there are some jets, because it's perforated place, the jet formed above the holes, velocity is non-uniform, and it only becomes uniform when the flow enters the flame. So that in that case we just measured temperature of combustion products in thermocouples and applied the same conservation, the continuity to the hot products boundary, and then just when you measure this temperature, it's you can get similar expression. So with that experiment, we actually found that plasma doesn't affect the flames. And mentioned temperature field. Actually, for temperature field, the same. Also for steady state flame, you can use the same continuity equation, except this case you are not tied to the flame. You can just use any cross section at any location, and then this continuity equation. You just in this case you just only need to need to know the only vertical component of the measured velocity field, and then you just get from ideal gas law, you get very simple relation. But if you select stream tubes thin, then every small disturbance on one vector will affect the whole stream tube. That means it's only possible with high quality measurements, which is still possible to done with autocorrelation method, for example. And there's another example which actually for which stream tubes was never used, and I never worked with that. It's so-called counterflow flames. So that flames are used for study mixed, for example, flames, and there's flow of opposite reactants, and there is stagnation plane, and the flame the flame is stabilized parallel to. Yeah, there are typically if it's premix flame, two parallel flame fronts, and with a constant stretch rate over the flame front, and with there like quasi 1D flame for the large part of the central flame. So the way the burning velocity, it's not burning velocity, but some value relevant to that is measured is there is a the profile along the central line is measured, then because of the stretch this velocity decreases, then because of thermal expansion it decreases, and when combustion finished again because of stretch it decreases again. So as a reference value, the velocity at the minimum is taken, which is already affected by thermal expansion, because otherwise there would be no minimum. And characteristic stretch rate is taken also. This is close to that boundary, the maximum stretch rate, which can also have significant variation of the flame. And so far, what I found that this burners were used to determine normal burning velocity for stretched flame, unstretched by extrapolation. However, these values themselves don't make much sense. They also depend. This location depends on the stretch, as I mentioned. Depends on thermal expansion, but this is actually ideal tools to study flame stretch effects. And for that, you need to know burn velocity here, or maybe just at the reaction zone or after reaction zone. Also, if you're interested in the stretch distribution or the flame thickness. And actually, this is kind of advice. Maybe someone works or will work with such flames. I didn't, and never did and probably will not do that. But I was always wondering why stream tubes method is not applied here, because here, because of it's quasi 1D flame, you can just select very wide stream tube, just single one, and because it is wide, the error will be small, and then you can use this. Also, all isotones, flame fronts are horizontal, and then the burn velocity takes the simplest form of this, and just I was surprised why not to is never used. Also, you can I think to recover temperature with this quality, because it's also quasi 1D. You can also select wide stream tube, and with temperature you can define any location inside the flame to which you want to relate your measurements. Okay, that's all what I want to say about the particle efficient symmetry. And another method, which is relatively simple, is the interferometry. For some reason, it's almost never used in combustion. There are many publications where you can find a illustration that you can measure temperature field of flame, but this can be understood for gas flame, because for gas flame you can have other methods like relay, which is easier to do maybe, and then you don't need less processing get result. But many flames like dust flames or liquid aerosol flames or flames in which you have nanoparticle systems, you cannot apply relay for them. And it seems to me like that for such flames nothing can compete with interferometry. But it's, as I said, it's very rarely used, and just want to say that like some things which you don't actually need to know much about it to apply it. You need to know some basic things. So how interferometer works? This is one of the most popular configurations about standard interferometer. So you have coherent light source, which is usually laser, can expand beam, makes parallel, then split on two. Then they travel different itineraries, but then you combine them again in one beam. And if you have very good optics, you have flat flame fronts, and this phase distribution is uniform. If you on any cross section, you can put screen here, and you just have uniform black or white background. But if you put flame here, then the flame changes, because density changes refraction index, and if this flame, the gradients are not strong, then you can assume that light still travels along the same rays, and then the flame introduces their phase shift, and between the measuring and the comparison beams, and then with this phase shift is equal like 2 pi times n, and then you have like black fingers at every location. Then you can, for every cross section, you can just find phase shift distribution, radial phase shift distribution, and then it's connected to local refraction index. You use Abel inversion, and you get local refraction index, and using just Glasson-Dale ratio, which says just refraction is proportional to the density with some Glasson-Dale constant, which usually doesn't change in the flame, so that you just recover the flame temperature. This works for flame with small gradients. However, if you have premixed flame, the gradients are very strong in the flame front, and then these gradients cause deflection. You can still think in rays terminology, even so it's not geometrical optics, but it works here. So that the deflection of the ray. So then this like ray was supposed to be produce interference with corresponding light of the comparison beam, but it declines, and actually this phase shift now you see on a wrong location. So your interferogram can still look good, but if you recover temperature field, it will be wrong. And this is something, it's so common error that almost all setups which so that they just don't do anything with that problem. And that why maybe that's why, because there is not so many publications about premixed flame. So but it's this problem is easy to fix if you put imaging lens which images the flame itself. So you may not see the flame, but it's supposed to image this plane on the sensor or the film. Then actually it can be seen that then the corresponding beams rays will interfere at corresponding locations, because the lens actually it returns this deflected rays back to corresponding location. So that's in this case you can do correct measurements. And there is just mentioned another very popular configuration of the interferometer. It's Wyman Green interferometer, and this is just better not to use for flames, because in this interferometer the laser beam actually travels twice through the flame. So, and then to compensate for that deflection, you need to image simultaneously actually flame itself and its image in the mirror, which is not possible with this lens. So that you always will have error with that. Okay, then once you have focusing lens, you can take advantage of this. Put iris here. This way you filter almost all flame radiation, or if it is like dust flame, you almost all scattered light will be filtered, and then if you not enough, you can put narrow band pass filter. There's another modification of this method is called interferometry in fine fringes. So if you don't align perfectly these mirrors and make this mirror like put it at a very small angle, then you already introduce phase shift, which changes linearly with the coordinate along the sensor, and you have pattern of nearly parallel fringes. When you insert the flame in this, these fringes will deflect, and actually their number of fringes by which it deflects is the same as number of fringes discussed before. That also corresponds to the phase shift. And the advantage of that your optics may be not perfect, because even so, if these initial fringes are not quite straight and parallel, you always have count fringes starting from this background. So you have to take one image with flame like this, I just forgot to mention, another without flame, and then you just compare fringes position. And this is an example of using this fine fringe method with Mach center interferometer. Actually, this is a burning magnesium particle, and the whole interferometer, I built this interferometer just with single purpose to study this particle. So it was adjusted to this particle. So all this this is actually the brightest flame. Maybe you can see it, and you need this iris, you need the filter, bandpass filter, even use polarizer to remove this radiation, on radiation and scattering. And scattering is extremely strong because it produces nano-oxide particles, and the region of maximum concentration, the beam attenuation is about 50 times. So for that to see, still to be able to see interferogram, instead of 50% mirrors, 70% mirrors were used, and they just split intensity between two beams like the ratio 1 to 5. So a much stronger beam was sent through the flame. And that this is the picture which is from the publication. At that time that photo were not produced with good quality, but actually fringes were seen everywhere. And what you can see, but maybe not also well seen here, but fringes are bent downward in the regions where nanoparticles are present. And this is because nanoparticles also change the refraction index. Always should be taken up. And the major purpose of this interferometer was not the gas temperature, but to measure concentration of nanoparticles. Volumetric fraction of nanoparticles, it's very hard to do it by any other method. So then here you can see refraction index recovered from the interferogram, and there is a very deep minimum where the nanoparticle condensation zone is present. Also, this is the temperature, which outside this condensation corresponds to real gas temperature, but inside it's a fake temperature. So by extrapolating this refraction index to this narrow zone, we can find contribution of nanoparticles, and from the theory of Landau that we can determine the contribution in the refraction index, and then can recover the volume fraction. And why we wanted to do this? We wanted to know emissivity of these nanoparticles. We also measured the energy, total energy of radiation, and I found that this emissivity is 3 orders of magnitude higher than predicted by theory, just not the theory, but also by experiment from conductivity of aluminum oxide. So, and that was important results which could not be explained like by general physics. So my colleagues, Yuriy Shoshin published a series of papers. He's a theoretician, so he just was able to explain it based on by using quantum mechanics. So it's interesting that this burning particle contains so much physics. So when holography just was discovered, soon after that, the holographic interferometry was developed. And first, just a few words how hologram works. Usually, you have some beam which you can always reproduce, some simple parallel or expanding beam, and you illuminate some object, or you have transparent objects illuminated by the light from the same laser. So they are coherent, and they produce interference pattern in every location where they intersect. So if you put a photographic plate here, and you actually fix this interference pattern and develop the film, put it back, and if illuminated by reference beam, then you create like secondary sources, which according to Huygens principle can actually radiate the same light as was falling on this screen before. Then actually what you see is you don't see objects, you see light actually. And then if you look here, if you have the same light wave as one was traveling from the object, you see it seems that you are looking at some object. And in holographic interferometry, the holograms of transparent objects recorded. So they are if you make, for example, 2 parallel beams, and you record just hologram of these 2 beams, and then you put your flame in one beam and record it again on the same hologram. Then when you illuminate by reference beam, there are actually 2 wave fronts recovered simultaneously, one with flame and one without flame. And then, regardless of the quality of the reference beam, or also this object beam without flame, you always get interferogram. So that can be even flame in the tube, for example, but you still get interferogram. So that's just an example of using holographic interferometry. In old times, it's like maybe 25 years ago, that which is just holographic film. Then let's see here, the temperatures of Bunsen dust flame was measured. This example is aluminum flame, but we also use zirconium flame. At that time, there was a very big discussion about radiation heat transfer, which considered to be important in small laboratory flames, but there were no measurements because it's very hard to measure something when you have dust. And this method allowed to just find out that there is no preheating actually inside the flame. It's practically room temperature everywhere. So then I did this many years ago, but then I thought, okay, now there are these digital cameras, probably something is going on with probably some digital holographic interferometry exists, and I found indeed like tens or maybe hundreds of papers about that. and many of them actually, to take flame as example, examine flame, but I saw no one. This all publications are done by groups which work on the diagnostic method, but I don't see any publication of people who do flame research applying that on any of the. And why I think this happens, because in digital interferometry, you don't need to develop films, you need to recover it physically, which is advantage, but you cannot actually recover the interference with laser beam. You have digitally model how flame would propagate from these holograms if it's illuminated by a reference beam. And this is just need software which is based on very complicated equations, and there is no commercial software or free software of this kind. You have to learn all this, write own, and I think most of people don't want this. Another thing that most of these setups, they don't allow to produce focused image, which is important for premixed flames, and all examples they show now just diffusion flames. But you need also to be able to do focusing. So then I was thinking that after that I read all this, I was thinking, is it possible to avoid this reconstruction procedure? Then this measurement could be made simple. Actually, if you don't have this diffuser in your setup, locally these two interference waves, reference wave and object wave, are nearly parallel, and they produce a pattern of nearly equidistant fringes. And exactly like in finite fringe method, when you have your non-flame, it distorts this picture. So you have two holograms, one with this without flame and flame, and they are slightly different. And so if you add two such patterns, you get so-called Murray pattern, which you often see like in new office chairs, for example, when two meshes. So I was hoping, okay, then I will do the same with holograms. So I built interferometer, made this holographic images, and then they added them, and I saw nothing. So it was like dirty spots on before and after. And why it happens? Because, for example, in office chairs you have fibers which modulate like nearly rectangular way, and when you overlap two such patterns, then you some locations you block light completely, and but here when light waves interfere, they produce sinusoidal modulation pattern. And if you add two functions, like the simplest way case, it's 1 plus sinus x plus phi 1 and plus phi 2. If you add them, then you get function 2 plus sinus plus phi 3, and then this average value of that is always constant, regardless the phase difference is always good 2. It may be constant intensity 2 or modulated, but average value 2, and you don't see the fine modulation. That's why you cannot see it. So that's the interferometer I built, actually quite similar to one I used before, but the difference is angle much smaller between the two beams, because the cameras, digital cameras, still have much worse resolution than holographic. And if you magnify on some small piece of interferogram, you see that there are these interferometric fringes. There are these patterns here. And if this is the sum of two interferograms, and you can see they're still here, but in some locations they disappear because the pattern overlap in the opposite phases. And it means that the information about this interferometric fringes is here. You just need to recover it. And then just one first way try to recover. First, we have like this low frequency modulations because of light intensity on the holograms, but we have also high frequency modulation. First, we can improve hologram just using pass filter which removes all low frequency modulation. And then you got this, and at a close look, you see that these are like grid patterns. And if you add this, you already see interferogram, just because when you apply these filters, the modulation is not sinusoidal anymore. So there is some non-linearity. The only just can then smooth and then enhance contrast, and you get interferogram. But there is an even better way. This is so-called the standard deviation function, which can be applied to two images. So it looks for deviation from the average image. And then when the two bits in phase deviations are nearly zero, they are minimum, but when they opposite, they are maximum, and you just get directly the image of interferogram. So, and this quality of that is, I would say, not worse than you can find in other publications. So this way you can do interferometry just without using this software or writing this software. The only important thing that it should be, as mentioned before, the image of the flame should be focused on the sensor. Okay. Now another like no, it's called method or but it's simple experiment just for also flame diagnostic. It's frame radiation loss measurement, and also for some reason you can very it's done very rarely, even so it's even for glass flame, it's recognized that radiation is important and can be crucial for like limit flames, like counterflow limit flames. So when you study flammability limits, but it's never measured. It is present in quite many models, but experimental measurements of this is quite simple. So first you need to have a good photodetector, and then like two types of photodetectors which you can use for that. One is so-called thermopile detector, and another is pyroelectric detector. Both the drawback of both, they have a long response time, like no further 1 second, but for example, for steady state flame, you don't care about that, and even for some, we'll talk about this later, your flames, you still can get integral power of the non-steady light source, like burning particle. So then this flame sensor should be have nearly flat response over a wide range of wavelengths. For example, this one covers from 0.2 to 20 micrometers, which is more than enough. And also the area of sensors should be large enough, because you always should put precise aperture in front of this, because this manufacturer characteristic that the sensor area is this, it's not a precise value. So just I used thermopile detector in my measurement, and just some more words about this, what it allows to do. If your thermopile detector is just two coaxial discs with connected by a series of thermocouple, and then the signal you measure is the sum of this signal from all thermocouples, which is proportional to the temperature difference between thermocouple ends, which in turn is proportional to the heat flux between this location. And then, so the all thermocouples signal is proportional to the total heat flux between the sensor and body, central area and the body of the photodetector. So they're designed to measure short pulses and the continuous. So designs mostly for lasers. And for short pulses, if you have short pulse, much less than detector response time, then it always reach some, regardless of the length of the pulse, it reaches the maximum, which is proportional to the energy of the pulse. And for long constant radiation, it just reaches some plateau. You can measure both. But what if your signal is comparable to the response time? Well, actually, if you look at the physics, how it works, the signal always proportional to the heat flux. And then if you have some radiation source which turns on and then off, like burning particles in some time, so that at the beginning signal is 0, and finally all heat should leave this area and signal again becomes 0. And if you integrate heat flux from this area, you just get energy. So that means that you can use this method by integrating a signal, which is like shown by blue line, to use total emission energy regardless of the shape or the length of this pulse. You will always get energy. So it's interesting that I asked actually manufacturers of this thermal pulse detectors, and they say that it's not possible to measure such sources, and then we have to do our own experiments which confirm that actually they measure with the same precision as a constant radiation flux. Then how to measure actually for radiation flux for different flames? The simplest way thing is to measure total flux for some flame which is optically thin. Then you just put your sensor at large enough distance. You can consider it a point source. You put precision diaphragm. You define solid angle, and you measure energy or power. And you know this solid angle at which you measure, then you just normalize it by the total solid angle, and you get value you want to measure. But sometimes you need to measure radiation of the flat flame front, or for example, the fragment of the flame front, like in the Bunsen flame front. And then the value of interest, in this case, interest is power radiated by the per unit of the area of the flame front. And this also causes often causes a lot of confusion, because when people want to measure this power, they look at the this terminology like radiosity, luminosity, irradiance, which all formulated for material surface. But this is not material surface. So you still may use this terminology, but all relations will be different. So better just to forget about this terminology and use just base principle. And this is just example how you can derive actually this relation. It is strict derivation, but it doesn't use any equations, any formula. So if you have flame front and you have screen, you have some aperture through which you look at the flame front. You can imagine like extend this flame front and this screen to infinity. And what it's obvious that all radiation which leaves the flame front to the right, to the right, then will fall onto the screen. Also, if you select any small solid angle, all radiation which is spreads within this angle also will finally fall on the screen. It means that actually it doesn't matter how far is the flame from the screen. Radiation distribution at the screen will always be the same. Means you can imagine that your flame is directly on the screen. It still will be the same. Then you just remove part of the screen which correspond to your aperture, and imagine your flame is directly here, so that you know the flame area which emits, and you know that's optically thin that flame, so you can consider as a point source, exactly like for the points small the integral measurements, and then you just can derive this simple relation, because the intensity of this point source is proportional to this area, and the intensity receive the detector proportional to that area. You have to normalize the times and you get this expression. But if you assume that it is a material surface, this coefficient, I don't know, maybe 1 or 2, I don't remember, but it will be different. Even more simple thing is which is also often used for like aerosol flame or dust flames, is measuring of fuel volume or mass fraction by light attenuation. So simple it is. So there are like many errors is made also with that. But there are like very simple things to keep in mind to do correct measurement. Here it's like yeah, laser which beam is attenuated. Sometimes you need reference beam because if your laser is unstable, but many lasers are quite stable, you just use single laser and single photodetector. First thing, that photodetector area should be large enough to receive all the beam. Otherwise, small deflections of the beam will cause the fluctuation of signal. Second, okay, you want to just remove flame radiation, for example. You can put put it here the bandpass field. But the one very important thing which almost always missed, there is a lot of scattered radiation traveled in the nearly the same direction as the laser beam, which is also received by photodetector. So you need to put pinhole here. So and then if you do all this, your measurements will be correct. Okay. Oh, I forgot that I have some animation here. And laser attenuation can be also used to measure particle size for inline measurements of particle size. Actually, so this is the setup which we use for that. We used UV beam, near UV beam, laser diode. It's better than using laser because you avoid this all speckle structure. You can have uniform background, and also UV because we have strong thermal radiation of particles. Then it is much smaller in the short wavelength range, so you can get rid completely of that if you use bandpass filter, and you get shadow. You get shadow. Your particles are flying here in this like normal to this drawing plane, and you get particle. Then what is the traditional way to do to measure particle size? It's also used in microscopes. When you have microscope image, you do size distribution. It's always also the same way. Just use image, put some threshold, and then find the area of this threshold image. But this area will depend on the threshold value. Also, if your particle is not focused perfectly, you can make a big error. So that, but there is another way. This particle actually removes some light from the illuminating beam, and the amount of light of this the particle removes is always proportional to particle projection area, even if particle is out of focus. So you can measure much more precisely if you use that. Then just some words about how image should be processed in this case. Because if you do, okay, just come back to this traditional way, you always subtract background, because there always some background you should, on the image. But here, if you do this attenuation means you cannot do this, because if you just subtract background, you get like this, because you subtract background also from the particle shadow. So there are two equal particles, but if you integrate attenuation, it will be different. So that for that reason, you need to divide backgrounds, and then you get this image by background, and then you get equal like integrals. And then another thing that how to then you after you subtract background, you should actually integrate the whole attenuation. Then this is inverted image. So for inverted image, you integrate like positive values, but over the whole area of particle shadow. But how you define this area? You always have some noise, and then your threshold should be above this noise, and then it means that you lose some signal. So that because if without noise, your signal would be like that. And that means that you need first, okay, you supply threshold, then extend the integration area over some range. Second thing, that when you normalize, it doesn't, regardless you just subtract or divide background by background, you always get some negative values. And if you use image formats, they are most of them have only positive values, and you lose all negative values. Some cameras do it automatically. If you rely on camera can do even worse. And then it's better to always use text files instead of image files. Then you keep also negative values and your background average will be 0. So we actually made this error. This error can be strong. We made it error in our parameter where measurement where we have to integrate the light intensity on particle emission. So we integrate over that area, and oh no, we relied on the camera, and then it led to error, the maximum about 100 kelvins, which we later had to report. So that this is important for all cases when you have to integrate image intensity.
So we are running out of time.
Oh, okay. Maybe a few. Okay, just short.
Most important things.
Okay. Sorry. Yeah, that's even this doesn't fit on. So that I mentioned also that for gas flame relay scattering is a very good method to measure temperature, but usually it's applied only for flames without confinement or very big confinement where walls are very far from the flame, because the signal is very big. If you have walls nearby, you have a lot of scattering. But we actually found a way to apply to flames in very small confinement for steady state flames with very simple means. So just use a focused laser beam and do line-wise measurement, and then just made small holes in the tube in the confinement, used like blackened tubes and windows, and moved flame itself through that. So, for example, doesn't work. Okay, should. Oh, this is. So when you move flame, let's see that you and record this scattering with some frequency, like here we record this frequency to get 300 micrometer revolution. Then you can integrate intensity across this line and recover temperature along that line, and get just by stacking this temperature, you get the whole temperature field, which, for example, this is temperature fields measured for bluff body stabilized flames, and here like 15 millimeter tube. And this is a flames which stabilize in downward flow. So that's cup-like flames in like 30 millimeter tube, and these are in the tube of 12 millimeter diameter. It's extremely small, but still it's possible to do this Rayleigh scattering, which is a very like useful, let's say that trick. Yeah. Okay, there is something more, but not so important, maybe. So that's, thank you. I think it was not, it was a bit boring because there are no scientific results, just, but for experimentalists, I think that's more useful than listen for some years.
Yeah, I'm glad because you did somehow what Combustion predicted, that you can really explain the extra knowledge that you need to